Okay, let's try to tackle part C on B-4. How long does it take the pin to hit the ground? So we threw this pin up, and we know that he threw it up at 5 meters per second. It's going to go up, and then we figured from A that after 1 second it's going to be going at negative 5 meters per second, so down at 5 meters per second. And from past problems, we know, without any air resistance or anything like that happening, we know that at this negative 5 meters per second, it's the same height as when he threw it. Because it's going to take the same amount of time to go up as it is going to go down, and everything's in reverse. Here, the VF on the right side, this little dashed purple line on the right side here, the VF up here is 0, the VI is 5. Well, it's the flip-flop when it comes down. The VI is 0, and it's going to speed up to negative 5 meters per second, or going down at 5 meters per second. So with that little bit of information, let's now try to solve C. Because we can say, okay, after 1 second of traveling up and now coming back down, we've gone 1 second. Let's start the problem here, okay, of trying to solve for how long does it take the pin to hit the ground. So I'm going to come down here to C. Pin. Okay. So it's gone 1 second, we're saying. After 1 second of travel, it's gone up, came back down, and now we're going to start our watch again, and it's going to go and hit the ground. Well, we knew he threw this out of a window. There's my window, 12 meters above the ground, so it has 12 meters to travel. So I know the distance is 12 meters. I know the acceleration is going to be 10 meters per second squared. Okay, and since I'm saying I'm going to say acceleration is positive, it's going down. Acceleration due to gravity is going down. I'm going to say that's positive. I'm going to say this distance he's traveling is positive. That's key. We're going to say this distance is positive now. And we're going to say that the velocity is just 5 meters per second going down, starting right here. Okay, so this VI is 5 meters per second. This is after it's traveled 1 second. This is what we have. Okay, we're just going to add this 1 second to whatever time we find now. This is probably the most straightforward way of doing this. To make things easier, let's figure out how fast he's going when he gets down to here, because we could try using the equation d equals vi t plus 1/2 a t squared, but I don't want to do that because we have a t squared here. It can be simpler if we just solve for vf, because once we use vf we don't have to use this equation, because that's a little messy. So let's find how fast it's going when it hits the ground. We know the distance it's traveling, we know the acceleration, we know the vi. Now, you're saying, well, Mr. Casinger, acceleration is always negative. So it's always going toward the ground, so shouldn't we say it's negative? We could say the acceleration is negative, but then we have to say the velocity it's traveling is negative, and then we also have to say that this distance it's going, since it's the same direction as the speed and the acceleration, we have to say the distance was also negative. So you can make all three of these positive, or you can make them all negative. Remember, you have to specify what direction you're going at, whether it be distance, acceleration, or VI, velocity. So to specify the direction, you have to say it's positive or negative. So yeah, you can make these all three negative, or you can make them all positive. I'm going to do all positive. If you want me to do all negative, ask me in class tomorrow. Okay, so I can quickly show you. So now I'm going to solve for VF because it's going to make my life a lot easier. So I'm going to use the equation VF squared equals VI squared plus 2AD. Acceleration is 10. Distance is 12. We have a 2 here. Kind of going backwards. VI is 5, so 5 squared. So VF squared equals all this. So we get 25 plus 20 times 12 Should be 240, but I'm going to make sure I get this. 12 times 10 times 2. 240. Just want to make sure. Alright, so now we're going to have 265 equals VF squared. Right, so we're going to take the square root of 265. And I got to get my other calculator to do that. 265. And I'm getting, if we use, how many sig figs do we have here? We should have another one. That should probably have, we'll say that's 2, so I'm going to go ahead with 3. Now 16.3 meters per second. Alright, because that's not my final answer, so I'm not going to round it down yet. So that's the final velocity. Okay, 16.3 meters per second. Now I can use a much easier equation with time in it than this one up here. I'm going to use acceleration equals VF minus VI divided by time. I'm going to rearrange the equation, solve for time. This goes away, A, both sides. So I have T equals VF minus VI divided by A. Alright, now I can plug in my acceleration. In this case, it's positive 10. VF is 16.3 minus my VI of 5. T equals all that. Okay, so now we got 11.3 divided by 10 equals time. So the time is 1.13 seconds. Now, this time is not our final answer. We have to think back to what we were doing. We said, what time is it going to take? Whoa, quit scrolling. What is the time for it to go from this point down? That's 1.13 seconds. But we said it had already gone up because remember he threw his red pin up. So it went up and came back down for 1 second. So the total time of the flight of the pin is this 1 second plus the 1.13 seconds. So 2.13 seconds is the total time. That is D.